Hello, Gary Parker here. We're going to take a look at a confidence interval for a mean with the central limit theorem. So here I have a sketch of some of my work for this. The big ideas this week, since we've been playing with hypothesis tests for a while, are that the central limit theorem gives us a formula to predict what the standard error of the sampling distribution. So that is, it tells us what the spread is going to be like from the mean. And we can calculate that using the standard deviation of the sample here and dividing by the square root of the sample size. Now, to do a hypothesis test, we need a null hypothesis and an alternative hypothesis, and then we need some data. So in this case, I have some data, river temperatures over here. And in the past, the temperature of the river around the time of the year I was looking was supposed to be about 10.5 degrees Celsius. And I suspect that the river temperature is higher. So my null hypothesis is that the true mean of the river temperature around the time I was looking was 10.5 degrees Celsius. And my alternative is that the true mean is actually a little bigger, maybe a lot bigger than 10.5. And so I need to measure to see if the average temperature of the data I collected from the river is significantly higher. And you can see here, I drew these loops down here. So I'm guessing like 1 standard deviation away from the middle, 2 standard deviations, 3 standard deviations. If the data shows that we're only about 1 standard deviation away over here, that's not that different than the center. We expect some deviation. Nothing is always perfectly the same. There's always a little bit of random variation. So if we fell in this region over here, we would say, yeah, you know, it's pretty close to what we predicted it would be. But if it falls out on the fringe over here, then whoa, that's higher than usual. Or if the temperature fell down here, we'd say, well, that's a little lower than usual. So it depends, how far are you from the middle? To figure out how far is too far, you have to run a hypothesis test. Part of that is calculating what's called the test statistic. Now, in general, a test statistic is the value from the sample. So here, my X bar is my sample statistic. So you take your sample statistic, you subtract whatever the value from the null hypothesis is, and then you divide by your standard error. And that's the general formula for a test statistic. And then the specific formula depends on whether you're doing a mean, whether you're doing a proportion, maybe you're testing for correlation with 2 numerical variables, and there's a bunch of other things. But mostly we're going to play with means and proportions, like this week, for example. So this over here is the specific formula for the test statistic for a single mean. So in my spreadsheet and in stack key, I said, all right, find me the mean of this data here. And I subtracted the value of the null hypothesis divided by the standard error, and I came up with a T or Z score of 3.24. Think about that 95% rule we learned way back in week 1. 95% of the values we expect to find within 2 standard deviations from the mean. And this says I'm over 3 standard deviations above the mean. So that's unusually high. So let's look at the spreadsheet version of this. So I have a spreadsheet that I've shared in several of the videos, and the link to the spreadsheet is below. So if you haven't entered it recently, you should. And feel free to make a copy of the spreadsheet and reuse it. That's what it's for. So I took the hypothesis test mean with data, and I duplicated it, and I renamed it hypothesis test river temp, and I just pasted my river data in here. And then the spreadsheet pretty much acts on its own for a lot of this stuff. It'll calculate the size, how many numbers were in there, it'll calculate your mean, sample standard deviation. You have to tell the computer what alpha is. So are you going to use the standard significance level of 5% or something else? And that's so we can decide, make the right decision. And then you have to decide on what your null hypothesis test value is. And in this case, I was told that we should expect to find the river temperature around the time I look to be about 10.5 degrees Celsius. So it's an equal to. Remember, null hypothesis is either equal to, greater than or equal to, or less than or equal to. So I put those symbols there in case you want to swap one out. So if somebody said the river temperature should be at most 10.5, then I would take that symbol there and plop it in place here. And that says the population average is at most 10.5. And that's just up to you. And then you have to decide what's your alternative hypothesis. And I was suspecting that the average temperature was higher than what it used to be. And so here you can see my mu is greater than 10.5. And I have it set up so you just type your number here. So maybe somebody said it was 11. The spreadsheet says, oh, okay, let's make that 11 too. All right. Standard error. Standard error, let's look at that, is the sample standard deviation here divided by the square root of the sample size. And you can see that's what my formula calculates, pretty standard. And then the test statistic is that fraction I was talking about, where you take your sample mean, in this case, sometimes sample proportion, divide by the null or minus the null hypothesis value. And then after that subtraction, parentheses are necessary, then we divide by that standard error there. And so there's that 3.24-ish number that I found. The p-value, show that in the picture again. In this case, I had to decide to do the right tail version. So you have to use the right formula for that. And my other versions of this spreadsheet have the left tail calculation, the right tail, and the two tail. You have to decide which of those is the right one for your particular problem. And so I just deleted the other two because I only wanted to see the right tail. Back to my picture. So here I have a randomization hypothesis test, and I superimpose that t distribution on top of it. See that smooth curve kind of running on top there. And the randomization hypothesis test said the p-value is 0.00057. And the randomization p-value is always going to be a little bit different than the spreadsheet calculation. So this was 0.002. And if I go to stat key and I run this again, so I'm going to copy the spreadsheet data, just the data, the raw data, and we're doing a randomization hypothesis test for single mean. I'm going to edit. Hopefully you've done this many times by now. Delete first is my recommendation, then paste it in. And notice I do have a header at the top here, but I don't have a first column identifying what each of those numbers is, so that stays unchecked. Null hypothesis A98.6. What was it here? It was supposed to be 10.5. Critical that you set this, otherwise this is worthless. All right, and then that redraws the correct dot plot there. And then once we have our data and our null in there, then we can go and generate new samples. And when we run a randomization hypothesis test, it's always going to be centered on the null value. That's important. It's not centered on the sample value like a confidence interval. Hypothesis test center on the null value. See that 10.5 in the middle there. And then we decide right tail test. Then we have to enter our sample mean down below here. Which stat key also calculates. Now notice I got a little bit different number than I got last time I ran the randomization hypothesis test, and it's not quite the same as the value the spreadsheet gave me, but they're in the ballpark of each other. 0.001, this one was 0.002, so 0.2%, 0.02%, and then that first hypothesis, randomization hypothesis test I ran was 0.0057. You might ask, which is the right one? They're all right. Answers vary due to randomization, and that's okay. They're in the ballpark. They all say reject the null hypothesis. That's the bottom line here. My p-value is small. My test statistic is 3 over 3 standard deviations above the mean. All those things are saying reject the null, reject the null. And so then I would have to come up with my conclusion. Now the conclusion that you come up with depends on your alternative and your null hypothesis. So in this case, we're rejecting the null, which means our data supports the alternative here. So we just need to write a sentence that says that, something like, we have significant evidence that the average river temperature is greater than 10.5 degrees Celsius. That's the conclusion, right? What does this mean? I got to go report back to my boss. What did I find? I said, yeah, the average temperature is higher than 10.5. And he says, okay, well, what's the average temperature? Well, I don't really know that. This sample had an average of 12.5, but that's just this sample. Every sample is going to be a little bit different. So if we wanted to then redefine what we think the average is, then we have to run a confidence interval. So let's do that for fun. So we ran our hypothesis test, and I did both the central limit theorem version, which basically, again, the central limit theorem just says this is how you calculate your standard error. And you can either do that on a calculator with stat key, because you need these summary statistics, right? You need to know the standard deviation of your sample. So either you have to go to stat key to find that, or you're gonna have to go to a spreadsheet. So typically if I'm using the central limit theorem, I'm gonna jump into a spreadsheet. And so this spreadsheet, once I plug in my data, calculates my sample statistic, my sample mean, my sample standard deviation, verifies the sample size for me, so I can find the standard error, the t-score, and again, the t-score is what we call the test statistic. Test statistic. And my mean, my sample mean is also referred to as the sample statistic. And then we have the null value. So these are all important values. And then our p-value is the probability of getting a more extreme sample than the one we found, that 12.5 with a standard deviation of 2.82. All right, so next let's think about a confidence interval. Let's draw a little picture of it first. So our hypothesis test said, yep, the null hypothesis is not supported by the data, the alternative is. And so now we want to make a new estimate for what we think the population parameter is. So to do that, I usually like to draw a number line. And then in the middle for a confidence interval, is whatever my sample says. And my sample says that I'm approximating the population mean. So my sample with that, let's just call it 12.5 for simplicity. The stat key said that the standard error, I'm just going to approximate that. I think it was about 0.6. Let's double check, make sure I got that right. Standard error, yeah, about 0.6. Let's just go to 1 decimal point for now. We're just going to rough guess the confidence interval. And let's suppose our confidence level was 95%. If the confidence level is 95%, that means the Z or T score is going to be almost 2. It's going to be about 2. We'll recalculate that in a minute just to be sure. So what that means is for a 95% confidence interval, I want to go 1, 2 standard deviations to the right to get my upper value. And I want to go 1, 2 standard deviations, sorry, that's messy, to the left to get the lower one. So if I'm at 12.5, this is a standard deviation. So I'd go add 0.6 and then add 0.6 again. So that'd be adding 1.2 to that. So that's going to give me what, 13.7 for the upper bound. And then lower, we subtract 0.6, subtract 0.6 again. So minus 0.6, minus 0.6. That's going to give me what, minus 1.2, about 11.3-ish. So if my boss says, okay, well, what do you think the new temperature is? And I say, well, I think the new temperature is somewhere between 11.3 degrees Celsius and 13.7 degrees Celsius. Or I can say, you know, on average, because I just estimated my margin of error here to be 2 standard deviations, 2 standard errors, which is about 1.2. So in other words, I can say, I think the actual temperature of the river is about 12.5 degrees Celsius, you know, plus or minus 1.2 degrees Celsius. So there's 2 ways I can state the answer, right? I can state the answer with my point estimate plus or minus the margin of error. Or I could state my interval, right? Or I could say it's between the actual river temperature, somewhere between 13.3 and 13.7. And this is the average temperature, right? Spots within the river are going to vary greatly, right? You go to the shore, it's going to be different than at the surface in the middle, than at the bottom in the middle. And over time, it varies. So we're talking about, you know, over the breadth and length and depth and time of the river in whatever time frame I'm looking at. Like my guess is these river temperatures are probably in this region of northeastern Oregon, where I am, probably, we're talking March river temperatures there with some snow melt. Now, I was just rough guessing the confidence interval here. And remember, a confidence interval is an interval of values that I think the real population mean lives in. And I think it's somewhere in this range of numbers. Okay, could I be wrong? Yeah, the actual one could be out here or down there. I don't really know. I never know for sure. I think it's somewhere in there. To do this on a spreadsheet, we already have a spreadsheet tab to do so. Let's see. Oh, look at that. CI mean with data. So what I could do is I could just duplicate this sucker. So we could rename it CI river temp, and then all I need to do is replace my data. So I'm just going to first highlight this data and delete it, and then go get the correct data. The spreadsheet will do it for me. All right. So it just says, oh yeah, there's 21 numbers there, and that the average of those is 12.495. We knew that before. The standard deviation is 2.82, blah, blah, blah. Here it says the confidence level is 95, which is what I was guessing at before. Based on the sample size and the standard deviation of the sample, we get a standard error of 0.616, same thing we saw before. Remember, alpha is what the tails have to share. So I'll redraw this stuff here. And then this t-score here is different than the t-score before. This is called the critical t-value or critical z-value. And it is totally based on the confidence level. So reminder about where that comes from. So in order to make a confidence interval, and this is one of the big ideas for this week, because we now have a formula we didn't have before. Assuming that our sampling distribution is going to have a normal bell shape, which it almost always does for the work we're doing, we want to find some boundaries left and right that are the same distance from this center here, so that 95% of similar samples end up in this middle region here. So that means there's 5% for the tails to split. So if we take 1 minus 95% as a decimal, that gives us that 5%. That's what we call alpha. And then we cut that in half, alpha over 2. That's supposed to be an alpha. Bear with me there. Oops, that's 50%, not 5%. That's better. That gives me that 2.5%, 0.025 that goes in each tail. And that tail, and then 2.5% of samples in the histogram would go in this tail. And what we want to know is we want to know what these two numbers are. What's the t-score? And whatever this t-score is there, this one's just going to be the opposite of it. And StatKey can calculate that for us, or we can go to a spreadsheet to calculate it. And so I just asked the spreadsheet to find that. And if you take a look, it says it wants to know what is the tail probability. That's that 2.5% here. And then the sample size minus 1, which we also call the degrees of freedom. And that was covered in section 6.2 in the first two sections, I guess, first two sections. Once I have that, I can find the margin of error. And reminder about that margin of error, if we go back to my sketch, how that comes about. And remember, I rough guessed it over here. What I did was I assumed my t-score was about 2. And then that tells me how many of these standard errors I need. And that gives me the margin of error. So my margin of error here came from taking the 2 from t, it's an arrow, multiplying by the standard error, 0.6, and that's where I got that 1.2 from. So in general, margin of error is always your t or your z-score. That's usually called t star or z star multiplied by your standard error. So I just rough guessed it over here. And oops, I miscopied this right there. It's not supposed to be 13, it's supposed to be an 11.3. So let's go back and check it out here. So I can see my margin of error is a little bigger than 1.2. Again, I was rough guessing it. The t-score in this case is a little bigger than 2, so my margin of error is a little bigger. But then you can see here's 11.2, 13.8, which were in the ballpark of what I just rough guessed based on 2 standard deviations. So again, first hypothesis test. And this part, just this first part, is kind of like the application for this week. You're given some data, you're given some information about what was expected, and then you have to decide if it's different from expected. And that's whether you reject the null or fail to reject. So we reject the null when we get a result that's significantly different than what was expected. If we fail to reject the null, that means the results are close enough to what was expected. In this case, since I have a small p-value, that's unusual. I reject the null and support the alternative. And a conclusion is where you write in plain language what it means to support the conclusion. I took this one a step farther than your application by saying, hey, this is different, so what do we think about the population? And that's what a confidence interval tells us. Now we can say that we think that time of year, the average temperature of the river is more between 11.2 degrees Celsius and 13.8 degrees Celsius, which is 10.5 ain't in that interval, right? Okay, so more evidence that something's changed. All right, that's it for now. Hope this was helpful and I had sound on this time. Take care, do good math. I'll see you in the near future. Bye-bye.